Control Shift S. This video is designed for VGS. VGS is in Dominican Republic, or he's back. We don't know yet. Tonight everything. Tonight we will find out. Everything will be clear. Something like that. Now, let's change the topic. Go watch Andrew NG. This video will be short because I just want to refresh my brain. I want to refresh it because long time I didn't watch my ML course. Favorite ML course of all time happened in fall 2018. We are 2024 and I'm still watching it. Dude, this ChatGPT, it's getting scary.
Welcome to CS229 Machine Learning. Some of you know that this class I taught at Stanford for a long time. And this is often the class
Shut up, bitch, for a second. Are we going to start? We're about to finish lecture 12. Guys, I want to just start Kaggle, data science, machine learning. And you know what is it? Once I learn all of these, I apply my... This is apply. I apply. You apply. You apply data market on it.
So
let's go with my favorite instructor of all time.
actually,
You have it or no?
let
Or
me
you
use
don't
this
have it?
board.
Let's go, guys. Oof. Another marker changes this marker because the previous marker is already
Trick
used
that you
up.
can use in order to help your network train are initialization methods and normalization methods.
Wait a second, what were we Okay, so we were looking at these like coefficients and how to find them, loss function, right? And the size of the matrices. Cat, we want to find cat.
Let me use this board.
Or we want to say like nonlinear function, but structured way. So we have these layers of linear and then nonlinear
Trick
sigmoid.
that you can use in order to help your
Isn't it
network
great?
train
Isn't
are
life
initialization methods
fucking
and
beautiful,
normalization
guys?
methods.
It is amazing. We have ChatGPT.
So-
we have smartphone. We have a wallet
we
full
talked
of
about the
money
fact
and
that if
credit
Z
cards.
is too big or Z is too low in the negative numbers,
We
it
receive
will lead to
email. I
saturation of the
receive
network.
more than 100
So in order to
emails a
avoid that,
day,
you can use
and I don't
normalization
even
of the
check
emails.
them. Wow, my inbox is actually my spam folder.
So assume that you have a network where the data is two-dimensional. X1, X2 is your two-dimensional input.
Wow, 2-dimension is so low.
You
So
can
I
assume
go solo.
that X1, X2 is distributed
Initialization
like this,
method. Like,
let's say. So this is if I plot X1 against X2 for a lot of data, I
yeah.
will get that type of graph.
Yes.
The problem is that if I
Yes.
do my WX plus B to compute my Z1,
X
if
plus
X's are
B.
very big, it will lead to very big Z's, which will
Big
lead
Z's.
to saturated activations. In order to avoid that, one method is to compute the mean of this data using
You
mu
compute the mean
equals 1
of
over
this
the
data.
size of the batch of data that you have in the training set, sum of xi's. So it's just giving you the mean for x1 and the mean for x2.
It
You would
checks
compute the operation x
data
equals
point.
x minus mu, and you would get that type of plot
Yes,
if you
removing the
replot the
bias.
transform data.
Removing the bias.
Let's say x1 tilde, x2 tilde. So here is a little better, but it's still not good. In order
Why
to
it's not
solve the
good?
problem
Well,
fully,
it's one
you're going to
also-
compute sigma squared, which is basically the standard deviation squared, so the variance of the data. And then you will divide by sigma squared.
We estimated 1 over n minus 1, or is it 1 over n? M, wow. X minus mu squared. Xi minus mu.
So you would do that, and you would make the
Well,
transformation of
this
x
is only
being
if
equal to
you
x divided by sigma.
center the data first.
And it will give you
which
a graph that is centered.
centered. It is centered. Render.
Okay. So you usually prefer to work with a centered data. Yeah.
You prefer. My data is already
Sorry?
centered.
Oh yeah. Sorry. Yeah. Correct.
See, I told you, motherfucker.
So if we subtract the mean of x1 and x2, it will be something like that.
I'm very centered. Namaste.
Sorry, it should look like this, but be centered. Okay, and then if you standardize it, it looks like something like this. So why is it better? Because if you look at your loss function now,
90% of them are
before
here.
the loss function would look like something like this. And after normalizing the input, it may look
May
something.
look, it won't be like
Something
this
like this.
exactly.
So what's the difference between these two loss functions? Why is this one?
Well, first of all, that is not true. I don't think it is true. What he's saying by drawing the circles, he's saying that these Gaussian, first of all, he assumes they are Gaussian. Then he assumes that these Gaussians are independent by assuming by the circle level sets, right? I don't think, nope, you should just x over sigma doesn't do the job. Well, you need to first of all center it, but you need to like do a inverse, like multiply it by inverse of a covariance matrix. Maybe.
Easier to train is because if you have a starting point that is here, let's say,
Or it's
your
square
gradient
root.
descent algorithm is going to go towards approximately the steepest slope. So you're going to go like there, and then this one is going to go there,
I think
and
this
then you're
guy
going to go
plays
there.
soccer.
and then you're going to go there, like that,
I wouldn't
And so on,
wonder if
until
he
you end
played
up
soccer.
at the right point. But the steepest slope in this loss contour is always pointing towards the middle. So if you start somewhere, you will directly go towards the minimum of your loss function. So that's why it's helpful usually to normalize.
That's nice.
So this is one method.
Well, we have to assume that our sigma inverse matrix is good enough.
And in practice, the way you initialize your weights is very important. Yeah.
Yeah. Yeah. Yeah.
Yes. So
Yes.
Hmm?
You go ahead.
exactly. So
Exactly.
here I used a very simple case, but you would divide element-wise by the sigma.
That's stupid. No,
Okay.
you don't.
So like every entry of your matrix, you would divide it by the sigma. Oh, one other thing that is important to notice. These sigma and mu are computed over the training set. You have a training set, you compute the mean of the training set, the standard deviation of the training set, and these sigma and mu have to be used on the test set as well. It means
Yes.
now that you want to test your algorithm on a test set,
Makes
you should
sense.
not compute the mean of the test set and the standard deviation of the test set and normalize your test inputs through the network. Instead, you should use the mu and the sigma that were computed on the train set because your network is used to see this type of transformation as an input. So you want the distribution of the input at the first layer to be always the same, no matter if it's the train or the test set.
Finish it. Finish it. Okay, 7 and 16, 23 minutes.
Here, likely, yeah. This
Yeah,
leads to
we
fewer
will finish it.
iterations.
We will finish it. what is name? So this
Okay, we have
one
a lot to
was
see,
the
so I will skip a few
backdrop
questions.
and we already finished neural networks. Debugging,
So let's delve a little more into vanishing and exploding
ML
gradients.
algorithm models and error analysis. Woo, that is sexy. Let's go. Next session is crazy. I want to finish this. Go for the next one. Debugging, like we already
So in order to get an
established our
intuition of
ML
why we
model
have this
and we
vanishing
wanna
and
do it.
exploding gradient
And
problem,
NG
we can
we wanna
consider a network
ML up
which is very, very
debugging
deep
and error analysis, expectation
and
maximization
has a two-dimensional
algorithm.
input.
Next one, EM, which
Okay.
is expectation maximization algorithm
And so on.
and
So
factor
let's say we have,
analysis.
let's say we have 10 layers.
Wow, dude, this is crazy. This is crazy. Lecture 16, independent
10 layers plus
component
an output.
analysis and RL, which is real life
So
or
assume
reinforcement
all
learning.
the activations,
Whole life is a
all the
reinforcement
activations
learning.
are identity functions, and assume that B's biases are equal to 0.
What are these?
If you compute y hat, the output of the network,
Is it like how many
with respect
layers?
to the inputs, you know that y hat will be equal to W
Continuous
of
state
layer L,
MDP.
capital L,
Lecture
denotes the
19,
last layer,
reward model,
times
which is the reward
A
of our work.
L minus 1 plus
Linear
BL,
dynamical
BL is 0, so
system.
we can remove it. WL times
Wow,
AL minus 1.
diagnostics.
You know that AL minus 1
Right, I
is
cannot
W
wait.
L minus 1 times A
How to
L
speak.
minus 2,
Wow.
because the
Sam
activation is an
Altman, the
identity function,
possibilities
and
of
so on.
AI.
Can
Wow,
back
guys,
up again.
how many videos?
You can go back, and you will
GPT-4
get
Oh!
that y hat equals WL times WL minus 1 times
Oh, they
blah,
have a
blah, blah,
course on
times
OpenAI?
W1 times X. You get something like that. Right?
Fuck it, dude. Don't
So now
distract
let's
yourself.
consider two cases. That L minus 2, U1 to 0.
What happened here?
And which
Okay, motherfuckers, let's focus.
okay,
There
we
are
have
a lot
to
of
see,
good
so
things in
I
the
will-
world, but they are
I will
bad
skip a
if
few
you get,
questions.
they make you distracted. This
So let's
20 minutes,
delve a
the
little
next
more into
fucking
vanishing
20
and
minutes is
exploding
for
gradients.
this fucking course. We have time, we have a lot of time for the future. Vanishing, exploding gradient. So,
So in order to get an intuition of why we have this vanishing or exploding gradient problem, we can consider a network
oh, vanishing slash
which is
exploding.
very, very deep
Mm.
and has a two-dimensional input. Okay? And so on. So let's say we have 10 layers in total. 10
Ooh,
layers
10
plus an
layers.
output layer. So assume all the activations,
What is a normal number?
All
for
the
layers?
activations
I
are
say more
identity
than 4,
functions.
it's stupid.
and assume that B's biases are equal to 0. If you compute y hat, the output of the network with respect to the inputs, you know that y hat will be equal to W of layer L, capital L denotes the last layer, times A L minus 1 plus BL, but BL is 0, so we can remove it. WL times AL minus 1. You know that AL minus 1 is WL minus 1 times AL minus 2, because the activation is an identity function, and so on. You can backpropagate.
Well, that is just
Can
being
go back,
linear. That's
and you will
stupid.
get that y hat equals WL times WL minus 1 times blah, 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 times W1 times X. You get something like that. Right? So now let's consider two cases.
Sigmoid.
Let's
What happens to
consider where
sigmoid?
the case where the WL matrices are a little bigger than the identity function, a little larger than the identity function in terms of
So they
values.
are scaling.
Let's say WL, including all these, so all these matrices, which are 2 by 2 matrices, right? Are these ones. What's the consequence? The consequence is that this whole thing here is going to be equal to 1.5 to the power L, 1.5 to the power L, 0, 0.
Yeah.
It will make y hat explode.
Infinite, yeah.
It will make the value of y hat explode, just because this number is a tiny little bit more than 1.
And if it is less than 1, it fucks it up.
Same phenomenon. If we had 0.5 instead of 1.5 here,
Vanish.
the value, the multiplicative value of all these matrices will be 0.5 to the power L here, 0.5 to the power L here, and y hat will always be very close to 0.
So what is the solution?
So you see, the issue with vanishing and exploding gradient is that all the errors add up, like multiply each other. And if you end up with numbers that are smaller than 1, you will get a totally vanished gradient when you go back. If you have values that are a little bigger than 1, you will get exploding gradients. So we did it as a forward propagation equation. We could have done.
By the way, I said linear, but we know that differentiation at the end will be multiplication of matrices. So
on it exactly the same analysis with the derivatives.
Derivatives.
Assuming the derivatives of the weight matrices are a little lower than the identity or a little higher than the identity. So we want to avoid that. One way that is not perfect to avoid this is to initialize your weight properly. Initialize them into the right range of values. So you agree that we would prefer the weights to be around 1, as close as possible to 1. If they're very close to 1, we probably can avoid the vanishing and exploding gradient problem.
Yeah.
So let's look at the initialization problem.
What if some of them are less than 1, some of them are greater than 1? And by the way, we don't want a lot of layers. That's stupid. I don't like that. I think it is against our values having too many layers. Let's have 3-4 layers. This way, I think too many layers will be a mental masturbation. That's it.
Example of the one neuron. If you consider this neuron here, which has a bunch of inputs and outputs on activation A, you know that the equation inside the neuron is A equals whatever function, let's say sigmoid of Z, and you know that Z is equal to W1x1 plus W2x2 plus blah 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 plus Wn xn. So it's a dot product between the W's and the X's. So the interesting thing to notice is that we have n terms here. So in order for Z to not explode, we would like all of these terms to be small. If W's are too big, then this term will explode with the size of the input of the layer. So instead, if we have a large n, means the input is very large, what we want is very small W.
Makes sense.
So the larger n, the smaller has to be Wi. So based on this intuition, it seems that it would be a good idea to initialize
1 over 1, okay, I will tell you. 1 over skew-RT of n. Because if they are like all random noises, we have the central limit theorem that says, is it central? Yes, it is central limit theorem. We also have law of large numbers. This is central limit theorem that says the variance will be sigma of skew-RT of n, right? Something like that. So I say Wi, set them 1 over skew-RT of n.
Wi's with something that is close to 1 over n. We have n terms. The more terms we have, the more likely Z is going to be big.
No, but this makes it too small. If xi's are random variables, right? 1. Some of them over n or over radical n have normal, I think it is over radical.
Initialization says the more terms you have, the smaller the value of the weights. We should be able to keep Z in a certain range that is appropriate to avoid vanishing and exploding gradients.
Let's see log force number.
So this seems to be a possible initialization scheme.
Central limit.
So in practice, I'm going to write a few initialization schemes that we're not going to prove. If you're interested in seeing more proofs of that, you can take CS230, where we prove this initialization scheme.
Yes.
Can I take down the board?
What is XN? Okay. So that means
So there are a few initializations that are commonly used,
exactly.
and again,
I was right.
this is very practical, and people have been testing a lot of initializations, but they ended up using those. So one is to initialize the weights. I'm writing the code for those of you who know NumPy. Not going to compile it here, but with whatever shape you're using, element-wise times the square root of 1 over n of L minus 1. So what does that mean? It means that I will look at the number of input. I'm writing n L minus 1 here, n to the L minus 1. I'm looking at how many inputs are coming to my layer, assuming we're at layer L. How many inputs are coming? I'm going to initialize the weights of this layer proportionally to the number of inputs that are coming in. So the intuition is very similar to what we described there. So this initialization has been shown to work very well for sigmoid activations. So if you use sigmoid.
Okay, that's something.
What's interesting is if you use ReLU, it's been observed that putting a 2 here instead of a 1 would make the network train better. And again, it's very practical. It's one of the fields that we need more theory on it, but a lot of observation have been made so far.
That's good. We just need the observation. As long
So
as
you guys want to do that as a project to see why is this happening? We would be interested. Okay. And finally, there is a more common one that is used, which is called Xavier initialization.
Isn't it Javier?
Which proposes to update the weights using square root of 1 over n L minus 1 for tan H. This is another one.
Oh, that's
and
N
another
of
one
L.
that is, I believe, called reinitialization. Recommends to initialize the weights of a layer using the Foring formula. So quickly, the quick intuition behind the last one. The last one is very often used. The quick intuition is that we're doing the same thing, but also for the backpropagated gradients. So we're saying the weights are going to multiply the backpropagated gradient. So we also need to look at how many inputs do we have during the backpropagation. NL is the number of inputs you have during backpropagation. NL minus 1 is the number of inputs you have during forward propagation. So taking an average, a geometric average of it.
I didn't understand this part, but doesn't matter to me. Go ahead, brother.
And the reason we have a random function here is because if you don't initialize your weights randomly, you will end up with some problem called the symmetry problem, where every neuron is going to learn kind of the same thing. To avoid that, you will make the neuron starts at different places and let them evolve independently from each other as much as possible. So now we have two choices. Either we go over regularization or optimization. How much have you talked about regularization so far? L1, L2, early stopping, all that? Early stopping, everybody remember?
Regularization and optimization. Okay, I didn't hear this.
First, what it is? No. a little bit. So let's go over optimization, I guess, and then we will do some
I know
optimization depending on the
optimization.
time.
I know Lagrangian. I know gradient. I know maximize subject to. I know linear optimization.
So I believe
know
so far you've seen
simplex
gradient
method.
descent and stochastic gradient descent as two possible optimization algorithms. In practice, there is a trade-off between these two, which is called mini-batch gradient descent. What is the trade-off?
Mini bitch.
The trade-off is that batch gradient descent is cool because you can use vectorization. You can give a batch of inputs, forward propagate it all at once using a vectorized code. Stochastic gradient descent's advantage is that the updates are very quick. And imagine that you have a data set with 1 million images. 1 million images in the data set, and you want to do batch gradient descent.
That's too
You know
much.
how long it's going to take to do one update? Very long. So we don't want that because maybe we don't need to go over the full data set in order to have a good update. Maybe the update based on 1,000 examples might already give us the right direction for the gradient of where to go. It's not going to be as good as on a million example, but it's going to be a very good
Oh,
approximation.
we are going to use mini
So that's why most people would use mini-batch gradient descent, where you have a trade-off between stochasticity and also vectorization. So in terms of notation, I'm going to call X the matrix X1, X2, Xm, and capital Y the same matrix with Y's.
555.
So we have M training examples.
I feel
And I'm
they
going to-
keep 555 for 2 minutes so that everybody feel they're lucky.
Split these into batches. So I'm going to
11, the same.
call the first
It just
batch
so
X1
often happens
like
so
this.
often. Either it is my
and tip
muscle
X
memory
maybe T,
or
like that. And X1
I
can
don't believe
contain
it. But it's
probably
just around every day it's
X1
happening.
until
Fucked up.
X1000,
I
assuming
know.
it's a batch
Yeah,
of 1,000
they did the
examples.
same too. They did with their battery life. Everybody knows that. Everybody knows what they did with their battery life. And then they said no, and now they are telling it. This is true. They are keeping these numbers up for a long time.
X2 then will contain X1001 until X2000, and so on. So this is the notation for the batch when I use curly brackets.
Dude, it is so warm here.
Same for Y.
Warm.
So in terms of algorithm, how does the mini-batch gradient descent algorithm work? We're going to iterate. So for iteration t from 1 to blah, 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 to how many iterations you want to do, we're going to select a batch. Select a batch of xtyt. You will forward propagate the batch. And you will back propagate the batch. So by forward propagation, I mean you send all the batch to the network and you compute the loss functions for every example of the batch. You sum them together and you compute the cost function over the entire batch, which is the average of the loss functions. And so assuming the batch is of size 1000, this would be the formula to compute the batch over 1000 examples. And after the backpropagation, of course, update. WL and BL for all the Ls, for all the layers. This is the equation. So in terms of graph, what you're likely to see is that for batch gradient descent, your cost function J would have looked like that if you plot it against the number of iterations. On the other hand, if you use a mini batch gradient descent, you're most likely to see some.
Wait a second. Ah! You drew it. Okay. I expected it to drop faster, right? But the error should be higher, right? Probably. But he's drawing it noisy.
Something like this.
Mm.
So it's also decreasing as a trend, but because the gradient is approximated and doesn't necessarily go straight to the middle of your loss, to the lower point
But it
of the
should
loss
go
function,
faster.
you
though.
will see a kind of graph like that.
No?
The smaller the batch, the more stochasticity. So the more noise you will have on your cost function graph. And of course, if we plot again,
Finish it. I wanna play counter.
if we plot the
6
loss
fucking
function,
minutes.
this was
Let's
gradient
go!
descent.
6
So this
4
is the top
minutes.
view of the loss function, assuming we're in 2 dimensions. Your stochastic gradient descent or batch gradient descent would do something like that. So the difference is there seem to be less iteration
Well,
with the
there.
red algorithm,
Okay, the x-axis
but the
was
iteration are
iteration,
much heavier to
but
compute.
if he said
So each of the
time,
green iteration are going to be very, very, very quick, while the red ones are going to be slow to compute.
so there is like, yeah, if there is too small batch, then we have a lot of these oscillations, and it may take the same time as going right away. So, but there is a good size of batch that is called mini batch, that the number of oscillation and the number of computation multiplied at each time step is better than just directly going, but where
This is a trade-off.
you get it.
Now there is another algorithm that I want to go over, which is called the momentum algorithm.
Just momentum. It's all about
Sometimes called
momentum.
gradient descent plus momentum algorithm. So what's the intuition behind momentum?
And we go, I don't know. Isn't
intuition
gradient
is-
the same as momentum?
Let's look at this loss control.
Oh, momentum is does he mean by like a momentum of a random variable, like expectation of e to sx?
And I'm doing an extreme case just to illustrate the intuition. Assume you have a loss that is very extended in one direction. So
I want to
this
fall from
direction
back.
is very extended and the other one is smaller. You're starting at a point like this one. Your gradient descent algorithm itself is going to follow the following. It's going to be orthogonal to the current contour isotherm contour loss. It's going to go there, and then there, and
Contour,
then there,
yes.
and then there, and so on.
Mm-hmm. This is mini batch.
So what
right?
you would like is to move faster on the horizontal line and slower to the vertical side. So on this axis, you would like to move
slower,
with smaller updates.
I agree.
And on this axis, you want to move with larger updates, correct?
Mm-hmm.
If this happened, we would probably end up in the minimum much quicker than we currently are.
Mm-hmm.
So in order to do that, we're going to use a technique called momentum, which is going to look at the past gradients. So look at the past updates. Assume we're here. Assume we're somewhere here. Gradient descent doesn't look at its past at all. It just will compute the forward propagation, compute the backprop, look at the
Yes.
direction and go to that direction. What momentum is going to say is look at the past updates that you did and try to consider these past updates in order to find the right way to go. So if you look at the past update and you take an
not
average
too
of the past
complicated,
update,
I get it.
you would
yeah.
take an average of this update going up and the update after it going down. The average on the vertical side is going to be small because one went up, one went down. But on the horizontal axis, both went
Damn,
the same
this
direction.
is smart.
So the
actually.
update will not change too much on the on this axis. So you most likely
Yes, that's
do
smart.
something like that.
I like it.
if you use momentum.
Well, we have to do something.
Does it make sense, the
today.
intuition behind it?
I liked it. I like the momentum.
So that's the intuition, why we want to use momentum.
Momentum.
And for those of you who do physics, sometimes you can think of momentum as friction.
Momentum.
You know, like if you launch a rocket and you want to move it quickly around, it's not going to move because the rocket has a certain weight and has a certain momentum. You cannot change its direction very, very noisily.
That's it, dude. Finish it. Finish fucking today. 2 more minutes. I don't
So
breathe.
let's see at the implementation of momentum gradient descent. Oh, and I believe we're almost done, right? Yeah? Okay. So let's look at the implementation quickly. So gradient descent was W equals W minus alpha derivative of the loss with respect to W. What we're going to do is we're going to use another variable called velocity, which is going to be the average of the previous velocity
Okay, one more time.
and the current weight
Dude, even
update.
not 1 minute? Okay, this time I will go 1 minute.
So we're going to use that, and instead of the update being the derivative directly, we're going to update the velocity. So the velocity is going to be a variable that tracks the direction that we should take regarding
Ready?
the current update and also the past updates with a factor beta that is going to be the weight. The interesting point is that in terms of implementation, it's one more line of code. In terms of memory, it's just one additional variable, and it actually has a big impact on the optimization. There are much more optimization algorithms that we're not going to see together today. In CS230, we teach something called RMS prop and ADAM that are most likely the ones that are used the most in deep learning. And the reason is, if you come up with an optimization algorithm, you still have to prove that it works very well on a wide variety of applications before researchers adopt it for their research. So ADAM brings momentum to the deep learning optimization algorithms. Okay. Thanks, guys. And that's all for deep learning in CS230.
I couldn't. Oh, that was deep learning. With a deep breath, we learned deep learning. Alright, I loved it. I loved this 2 session. I know what I love even more, so let's fucking do it. We will do it for ten minutes. Dude, I like to have more fills. Oh, don't kill me, motherfucker. Motherfucker, go. Alright. Why did I do that? Oh, shoot. Where are these motherfuckers? scared, guys. Oh, motherfucker. Come here, come here, come here. Oh. Oh. Don't. Fucking don't kill me. Oh, let's shot. I'm glorious. Bitch, where are you? Don't. Motherfucker, let's go! Let's get up this fucking... Alright, I'm going, guys. I'm going to kill these motherfuckers right now. Bitch, oh, yeah. Alright. Oh, motherfucker. You're killing my friend. This one. Oh, let's go, bitch. Oh, I'm going this way. Motherfucker. Cheers to all of the motherfuckers. Ground. Take their life from them. How did you kill me? Oh, she got the fucking... I know, he will come here, he wants to kill me. Kunai! Dude, I just came. Well, I was pretty good. We had 2 bots. What are these? Kills, 12 kills. Wow, look at the first one, motherfucker. The only person whose kills are big. Wait, who are these new people? Shut up. Oh, let's go. I'm gonna fucking ruin their life, bitches. Where are you? You're all shop. Shut up, notorious. Who did you shoot, brother? I killed. Fuck you guys. Where is the chicken coming from? Oh man. All of our buddies are sick. Oh, we are the strong side of the story. Oh, shoot. Now they are going to kill me. Oh, motherfucker. You are going to kill them. Alright. Okay, wait a second. Why am I on the police side? I don't like that. Why am I on the police side? Three times in a row, motherfucker. Shout out to Notorious. Glorious. Dude, police is not good. Ah, fuck. Dude, I don't like him. Who chose me? what I want. Bitch, I'm going to kill all of these motherfuckers. Okay, now it's not the time. Turn it. Ah, fuck! I knew it didn't. Again, this motherfucker! Oh. Who's shooting us? We are slaughtering you. You come here to our field? Bitch. Since when? Who shoot? Fuck orange soda! Every time. Right, we are going to nail them. I was so dumb. It was me. Dude, counter turret is so strong. Do you know this? Motherfuckers are here. Who is shooting? Let's go, brothers. Fuck! I had him. Why did I do that? I wanna be. That's me. Let's go, bitch. How doesn't it kill? Okay, my buddies are on the run. So I can kill. What is this? And I am the lower is. Who killed? Let's go, okay. What did I expect? Like, I can see one of them. Fuck, give me some time. Ah, fuck off. Okay. Last round we are playing. Dude, nothing was left. Who is this guy? You bitch. Who is this guy? This guy is funny. This is like a shit show. Ah, fuck. Dude, this Nitro guy is really good. Like, we are killing them and he has the pistol. Whatever. Where's my... Oh, why did they happen? Just fallen angel. Where am I? Where am I? Where are my buddies? Doesn't seem like our neighborhood. Yeah, I came wrong. Let's go keep the pressure, guys. What? Oh, it is. What the fuck was that? Oh, who has the knife? It is right click, motherfucker. I didn't know that. Knife. No way! Who won? Shoot. Okay. Guys, 10 more minutes. It was so low. I didn't know that, to be honest. So we are doing 10 more minutes? Alright. Well, I just want to do one more field. Minimum of this new field and 10 minutes. Because I was I'm not police. I am police. Fuck. Oh, okay. Nice. That's better. It just took me a while to get it. Again, orange silver. Shout out to Notorious. How didn't I kill him? Bitch. Shut up. I killed. Hit him in the chest. How is that possible? Dude, this gun is disgusting, man. Oh, shoot. This guy gonna kill me. Oh my god, they have people who... Uh-huh. Fuck you, bitches. Oh, I have a body around me. That's it. I killed. Fucking Muro. Oh, bitch, shut up. Woohoo! I'm here with my boys. Oh, they're going to kill me like it. I'm gonna kill this one. Fuck. Fuck you, Muro. Easy. Sweet. What? Oh, okay. Ooh, guys, I'm ahead. Fucking. Let's go. What is happening? Oh shoot, I don't like this gun. Let's go. Don't put yourself on the gunfire. Woo, I killed. Yeah! Let's go. I killed. Fuck me, bro. Fuck you. Disgusting asshole. Kills me every time. Ah, bitch, what are you talking about? Oh, this gun is terrible. Alright. Alright. Let's be nice to each other. Oh my god, this is a shit show. Oh, this is not a... fuck, I thought this is the slogan. Shit, I was on the wrong. Let's give it here. Okay. Fuck Mura! Who is this guy? Again? This is a joke. Wait a second. Every time Muro kills me, I cannot move. What is this one now? Perfect. Fuck! I wanna kill them. Go ahead. Ah. Fuck this gun. Let's go. Let's go. Ah! Again! Oh my god! I wanna kill him one! Oh shit. What's happening? He will knife me. It is my nightmare. He will knife me. He will knife me. He will knife me. He will knife me. I know. This motherfucker will knife me. I tell you. This is a fucking oh shit, he's gonna knife me, I know. I promise, I swear to God, he's gonna knife me. Oh, it is, oh fuck yeah. Oh fuck. He's gonna knife me, no doubt. This is a no-brainer. We were... fuck, dude. Fuck. Massive, right? Oh, what is this 79? Oh. Yeah, Muro won. Well, okay, 8 minutes. We are quitting. It was... I mean, first time... Okay, just one more time, because it was like after a long time. I've never had this. Like, there was always bots on one side, and last time we also... You know what I'm saying? Last time... yeah. So last time it was really shitty. last time was too close. I loved it. Fucking Jesus. Who is this guy? What is this guy? Right as he is. I hate this gun. Okay, I love this gun though. They didn't expect that to happen, huh? Edge, I'm gonna kill you right now. Yeah, guys, let's go. Whoa, 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 what? How many of you? How many? They all got back home? Bitch. Which one? It is 20, so why did I? What do they have? They have some fucking guns. Where are you going? Didn't you see the cat? Shit, he killed me. Oh fuck, now I have fist gun. That's the most disgusting gun ever. Calm down. Where is this guy? What is this electricity? It turns me back to my fucking... I hate it. Alright, okay, we got my fucking gun back. Doesn't matter, to be honest. Which one are you then? Oh, they are coming, guys, they're coming. Oh, dude, last time it was right. Fuck! Honestly, I got him. Where are you going? Why am I here? And I am notorious. This guy. Oh fuck! This guy has knife now. Sit down, bitch. They will kill me. I killed him. Who got the knife? Motherfucker. Alright guys, enough. It was glorious. Okay. I loved it. It was so fucking close. Alright. Stop. Goodbye guys, goodbye.